Hello, everyone. Welcome to our Wednesday seminar. Today, we are very happy to have David Hosking from Oxford, and he's going to tell us about his recent work on primordial magnetic fields.
Thanks very much, and thank you very much for the invitation to come and talk to you today or this evening, as it is here in the UK. Yes, I'm David Hosking. This is going to talk to you today about some work completed as part of my PhD at the University of Oxford with my supervisor, Alex Chekshigin. There are two papers that this talk is kind of based on. One of them, this first one here, is kind of a physics paper about the decay of MHD turbulence and some new results. And the second one is a preprint which my talk follows, and is designed to apply this theory in the first paper to the problem of decaying primordial magnetic fields. So let me get started. So the first thing, I'm sure this is not news to anybody here, but just allow me, for the sake of introduction, to say that it is believed that cosmic voids, the voids of large-scale structure, host magnetic fields. So how do we know? Well, this fact comes to us actually as a non-detection of secondary gamma rays from distant blazars. So basically, the idea is if I have a distant blazar and it emits high energy TeV photons towards Earth. Now, as those photons propagate towards Earth, they pass through some cosmic void, and within that void, they scatter off CMB photons. They pair produce. They produce electrons. There's an electromagnetic cascade, and those electrons subsequently re-emit photons. Those photons, these are the secondary gamma rays. These photons, in principle, can be detected by gamma ray telescopes, but actually, these what's observed from the sort of Fermi telescope is that actually these secondary gamma rays are suppressed. They're actually not observed, and so this is interpreted. The question is, why does this happen? And one prominent interpretation of why this might happen is actually that the voids are filled with magnetic fields, and the charged particles, the electrons and the positrons that are produced in the cascade are scattering off these the magnetic fields, and therefore the emission of the secondary gamma rays is diffuse. They're emitted out in all directions, and therefore the intensity is reduced, and so therefore they're not detected by Fermi. And so, using this principle and modeling exactly how these electrons or how the charged particles are supposed to be deflected by the magnetic fields, one can derive sort of order of magnitude estimates of how strong the magnetic fields within the voids need to be. And this isn't a pure estimate of how a pure estimate on a pure lower bound on the magnetic field. It's sort of an inequality that relates the magnetic field strength and the sort of coherence length, the correlation scale of the magnetic field, because there's a degeneracy there in the scattering process. So you can have a stronger field, or you can have one that's correlated over longer distances. So assuming a stochastic scattering process, you get an inequality like this, where this 10 to the minus 17 is kind of an order of magnitude thing. And so there comes a question: where do these void fields come from? And so the first thing that you might expect is that perhaps these void fields were generated by dynamo, and that's typically where magnetic fields come from in astrophysics, at least in collapsed structures. However, within the voids, that's precisely where you wouldn't have flows induced by structure formation, and so dynamo is likely to be inefficient and perhaps not the origin of the void fields. Perhaps the void fields are actually a result of galactic outflows, and this, I think, is a view that many people do take. You do have galaxies present within the voids of large-scale structure, but it's I think fair to say that it's unclear whether their density is large enough and whether their outflows are magnetized enough to guarantee that one could fill a void with magnetic fields of the required strength. And sort of a more exotic suggestion is that actually these fields might be relics of magnetic fields generated in the early universe. So in certain models and certain theories, phase transitions in the early universe can generate so-called primordial magnetic fields, which would then become the seed for later dynamo action in the collapse structures. Now, in the absence of dynamo and pollution by the presence of galaxies, the relics of those primordial fields should in principle remain within the voids. And so that invites the question, how strong should those relic fields be today? And would they satisfy that observational constraint? So that's the question that I'm going to try to address, assuming that everything that I've said so far holds up and that the magnetic fields are generated and then they decay. How strong would their relics be? So that's sort of the physics question. So sort of to get us into this, I just want to start by talking about the sort of a much simpler decaying turbulence problem, which is the decay of hydrodynamic turbulence. There's no plasma, no magnetic fields. I just want to understand how the decay of kinetic energy happens in a sea of homogeneous and isotropic turbulence. So the theory of how to work out what this energy U squared is as a function of time was actually derived by Kolmogorov, like most important things in turbulence theory, actually in the third of his seminal 1941 papers. So the idea, you write down the simplest thing you possibly can, which is d energy by dt must scale like minus energy divided by the characteristic timescale for the decay. Now, what is that characteristic timescale? Well, dimensionally, there's basically only one thing that it can be. It's the correlation length, the size of the largest structures, the energy containing structures, divided by the characteristic velocity of those structures. So that's the turnover time of the largest eddies. Plugging that in, one finds that du squared by dt scales like minus u cubed over lambda. So at that point, you're stuck and you have to relate lambda to u in order to close your equation and solve it and then get a prediction for how u evolves. So the answer to this question of how to find lambda as a function of u turns out to be related to certain properties that are in turn related to the large scale structure of the turbulence, the large scale spectral power law. So it turns out that if one takes the formal expression for the kinetic energy spectrum, kinetic energy power spectrum as a function of wave number. So by the formal expression, I mean that energy is the Fourier transform of that the spectrum is the Fourier transform of the 2-point velocity correlation function, and one formally expands that in small k. The result, assuming that correlations decay sufficiently quickly, is the following expression, the following Taylor series, where that takes the form something times k squared plus something times k to the 4. And the something that sits in front of k squared is this integral here in yellow. That's called the Safman integral. And the integral here in front of the k to the 4, that's the Luytsansky integral. And it turns out that both the Safman and Luytsansky integrals are invariants of the decay. They're conserved quantities. And the physical reason for that is the conservation of fluctuations, so not net, but fluctuations in linear and angular momentum. So this was actually worked out firstly for the Luytsansky integral in the angular case by Landau, and later for the I think I'm right in saying later for the Safman integral by Philip Safman, and also Peter Davidson recently has done quite a lot of work on looking at nuances in Landau's calculation. But in a sense, to be made precise later in the talk, because this is going to be important, this mechanism, these integrals turn out to turn out to relate to conservation of fluctuations in linear and angular momentum. So that's something I'll come back to. But for the sake of the problem at hand, the invariance of these integrals and this expression that I can write down here implies an important principle, which is the principle of selective decay of small scale structure. So what do I mean by this? Well, I have a very high-tech graphic. If you focus on this spectrum here, that's what it means. As time goes on, the energy decays, this small scale structure decays while preserving the asymptotic, while preserving the k to 0 asymptotic, and that's because both of these integrals are conserved. So I've gone for a k to the 4 slope here to illustrate this. And the reason that I have is because it can be shown that provided correlations in the velocity field go to 0 fast enough in incompressible hydroturbulence, this Saffman integral must be 0. And so setting that to 0, you have a k to the 4 spectrum, and that's what I'm going to assume throughout this talk, actually, that correlations do go to 0 fast enough. But assuming that happens, this integral is 0, and the Lojzanski integral is constant. And so simply counting up powers of things in this integral, one gets a scaling. So look, I've got 2 powers of velocity here and 5 powers of length. So that's 2 powers here from this r squared and 3 powers from the volume element. I find u squared times lambda to the 5 is constant. So that gives me my lambda is lambda of u. I plug that in here and I find that u squared decays like t to the minus 10�7. So that's the Kolmogorov decay law for hydrodynamic turbulence. Right. So now, how do we apply this idea to the decay of magnetohydrodynamic turbulence and therefore to these primordial magnetic fields? Well, historically, the idea of selective decay of small scale structure has been conjectured also to control the decay of primordial fields, particularly in the absence of magnetic helicity. So that's when the helicity density, and I introduced this tilde here to represent a quantity that is properly rescaled into the conformal value of the quantity so as to account for the expansion of the universe. In my primordial problem, so the rescaled magnetic helicity, which is equal to the vector potential A dotted with B, so B is the curl of A, the magnetic helicity A dot B, then the ensemble average of that is 0. So that's non-helical magnetic fields. And so the idea is that actually the decay of such fields should be controlled by this selective decay of small scale structure. And apparently, in fact, this did look to be the case in early simulations. So here's a simulation that looks rather like that figure I just showed by Banerjee and Janamchik, 2004, showing you have this small scale, the large K structure is decaying, but the large scale asymptote is preserved. And so one can simply port those Kolmogorov results to the turbulent to the primordial fields problem. So one writes down dB squared by dt is like minus b squared over tau, and this properly rescaled b. Now tau, one argues, is particularly in the magnetically dominated case, again, there's really only, well, it would appear only one time scale that there can be. That's the alphenic time scale, which is the correlation scale of the magnetic field divided by the Alfvén speed, which is the typical speed to which the magnetic field wants to accelerate a flow, given by b over square root of 4 pi times density. And again, assuming that b squared lambda to the 5 is constant scaling law that would follow from the preservation of a k to the 4 spectral asymptote, one finds that b squared has to go like t to the minus 10�7, lambda has to go like t to the 2�7. So there's the prediction. Now, how does that compare with the observational constraints, the one that I mentioned at the start of the talk? So in order to answer that question, it's convenient to represent the decay graphically, as is often done. And so a nice way to do this, and is the conventional way, is to, although I'm not sure this is the conventional justification, but this is how I like to justify it, is to note that Well, if b squared decays like a power law in time, with p being just some number of order unity, then db squared by dt, well, this should perhaps be a scaling sign, is minus b squared over tau. But if I substitute b squared into here, using that b squared is proportional to t to the minus p, I bring over a p, but that's an order unity quantity, and so I find that t scales like tau, evaluated at the time that evaluated at time t. So what this means is that given that the final point of the decay at the time of recombination is much larger than the initial time, one can find the modern day field parameters as an intersection of the sort of conserved scaling line, b squared lambda to the 5 is constant, and t scales like tau. So this will become clear once I put on a plot. So this is a sort of usual plot that often people show of b tilde against lambda. And so what I mean is that the modern day state, or the state of the field at the end of its decay, is given by the intersection of the line that the field evolves along as it decays. This b squared lambda b to the 5 is constant line. Is given by the intersection of that line with this expression. This should be a t here, I think. T, which is the conformal time evaluated at recombination, being on the order of the alphenic time scale at recombination. So I hope that's clear, the intersection of those points. So one can also plot on this picture the gamma ray constraint. So recall that was something like b had to be greater than lambda, 10 to the minus 7 times lambda in megaparsecs to the minus half. And so that gives you a line that sort of comes down like this. And actually what one finds is that if one would like to have one's field generated at the electroweak phase transition, then it seems unlikely that one could generate a non-helical magnetic field that could satisfy the observational constraint. And the reason is that if one started one's decay with a correlation scale that was equal to the Hubble radius, and with a magnetic field energy that ensured equality between magnetic energy and radiation density at the time of the electroweak phase transition, one would arrive, following this decay theory, at a magnetic field strength that didn't satisfy the observational constraint. And actually, what's typically believed to be the case is that the kinds of actually magnetic fields would be more likely to be generated with a Hubble radius that was, sorry, with a correlation scale. If they were generated at the electroweak phase transition, that would be much smaller than the Hubble radius. Something like 10 to the minus 2 seems to be a canonical estimate. And of course, you see, if you start there, even with magnetic energy that equals radiation density, you end up way in this disallowed region. So this, this is not my result. This is the result, I think, of Wagstaff and Banerjee 2016. So they say that magnetogenesis of the electroweak phase transition results in modern day fields that are too weak to explain observation. So appears unlikely, they say. So this is for non-helical magnetic field, I should say.
Let's ask a question about this plot. So you have this gamma ray constraint. So anything below that line is a constraint. Now, what's the second line?
Yes, good point. Yeah, I didn't say that. So, as I said, that 10 to the minus 17 is order of magnitude, and the second line is just 10 to the minus 15, which is to show the range of values where that constraint could sit. I think that the paper that derives that 10 to the minus 17 says it can be between these things. Yeah. It's to show that it's not a precise thing.
Okay.
So there we are. So so where I'm going to go now with this talk is point out some problems with this theory and ultimately try to persuade you that a different theory should be followed, and that theory doesn't have this problem, and actually that one can have non-helical magnetic fields that are consistent with the observational constraints. So what's wrong with this? What's wrong with this sort of conventional treatment, the Banerjee and Jadamchik 2004 treatment? Well, it's based on this idea of selective decay of small scale structure, this conservation of that asymptote. And when you think about it, it's not actually that obvious that that this result should hold in MHD, because as I said earlier, the conservation of the Luytsansky integral is a consequence of angular momentum conservation. Now, there is no analog of angular momentum for the magnetic field. There is no R cross B invariant. The R cross U is an invariant, the angular momentum, but R cross B is not an invariant. And so formally, one can't say that the Luytsansky integral that you get if you simply change U in that integral to B should also be, there's no reason to suggest that that integral would be an invariant. And actually, it turns out that even in the modern simulations, so this is the 2015 paper by Axel Brandenburg and collaborators, it was found that if you go to sufficiently high resolution, if you go to large Reynolds number, large magnetic Reynolds number, actually this asymptote isn't conserved. And so actually the conservation, its apparent conservation in the earlier work was actually just a result of insufficient resolution, of insufficiently large dimensionless numbers. If you get yourself into the properly turbulent regime, actually this k to the 4 grows. This k to the 4 spectrum grows with time. So you can see that this dark black line, that's the magnetic energy spectrum, and you see some surrounding times in the pale gray, and you see that this k to the 4 asymptote goes up with time. So this was discovered by Brandenburg, and around the same time in kinetic simulations by Zrake. So how can we understand this, and does this have something to do with the well, it seems like it will have something to do with the shortcoming of the previous theory to predict consistent fields. So I note that inverse transfer, this growth of the spectrum, was previously expected in a different kind of turbulence. That's the kind of MHD turbulence that is net helical, the sort of parity violating kind, where you have a non-zero expectation value for H tilde equals to A dot B, and that by necessity is a magnetic field that has parity violation if that thing is non-zero. But enforcing that conservation gives, because A dimensionally is B times L, gives B squared times, or sorry, B times lambda, gives B squared times lambda is constant. And so if I ask what the scaling of that coefficient of k to the 4 has to be, so recall that that's proportional to B squared lambda to the 5, well, if lambda is like B to the minus 2, then this is proportional to B to the minus 8. And so you see that as B goes down, B squared lambda to the 5 has to go up. And so that's sort of the origin of the, or one way of arriving at the inverse transfer for a net helical field. But the problem, of course, is for the parity-invariant magnetic field, as sort of should be the default position of something that one might have at a phase transition, has vanishing expectation of the helicity. So, right. So this is kind of one of the key points of the talk regarding the decay of parity symmetric magnetic field. So the key point that I want to propose is that even if the magnetic field, a non-helical magnetic field, has zero net helicity, this need not be the case. And sorry, this should have these should have tildes. This need not be the helicity need not be zero everywhere. This need not be pointwise zero if this average is zero. The point is that the fluctuation level of the magnetic helicity in local patches is conserved, and this implies the existence of a new invariant. So you'll immediately notice that all this, so this is the new invariant here that I'd like to argue, I'd like to put to you. But you'll immediately notice that this is precisely the Safman integral with U ported or U replaced by magnetic helicity. So the claim is that this quantity encodes conservation of fluctuations in the helicity density in precisely the same way that the Southman integral, you'll recall that I said, conserves or encodes the conservation of fluctuations in the linear momentum. So let me explain how this works, and this follows the argument laid out originally for the Southman integral itself by Philip Southman. This quantity, incidentally, I call the Southman helicity invariant for this reason. So, firstly, the sort of immediate thing to note is that by equating or by treating the ensemble average as a volume average, one can write this integral in the following way. So IH becomes the limit as volume goes to infinity of 1 over volume times this integral here, which is actually just the square, which is actually just the helicity contained within the volume V squared, and then divide by volume and take the limit. So it's helicity contained within the volume squared divided by volume, limit as volume becomes large. So the idea is that if I pick a volume and I start increasing it, the total helicity, which is a fluctuating quantity, adds up, in a random way, and so h squared is proportional to the volume. But it's conserved because helicity itself is conserved, which means that any process that occurs entirely locally within this volume has to be helicity conserving. So this is like like fluxes of helicity round inside this volume, or sort of reconnections of structures inside the volume. That all has to be a helicity conserving process. The only way that HV can change with time is if there are fluxes occurring at the surface of this large volume, or if there are reconnections between structures occurring at the surface. And so therefore dH squared by dt scales like the surface area, or the surface area of this sphere that I'm imagining, or like volume to the 2/3 equivalently. So if one forms the rate of change of h squared, just using these two estimates here, one finds that thing is proportional to v to the -3rd, and so taking that limit, volume goes to infinity. This rate of change goes to 0, and so IH becomes constant. I think that's the most physically transparent argument for why this IH is a conserved quantity. Of course, if one prefers, one can just write down an evolution equation for H and construct the evolution equation for the correlator, and then integrate it over space, and that also you'll be able to show that this is invariant in that way. But I think that derivation loses something in terms of just the physical insight there.
Can I ask a quick question?
Please.
In the second line where you have the volume integral, isn't the expression in parentheses just the net average helicity in that volume? So if the volume goes to infinity naively, that should go to 0.
Yes, well, it should, in the sense that this divided by volume goes to 0, right? H on V goes to 0 as volume becomes large, but H squared on V, because it's made up of fluctuations, right?
There is an extra power of V, basically. Okay.
Yeah, that's right.
Okay.
So H is like V to the half because of the fact this adds up kind of as a random accumulating quantity. Yeah. So what does this imply? This conservation, right? So here's IH. Now H scales because H is A dot B, so A dot B scales like B squared times lambda. So we have 2 of those, and then 3 extra powers of lambda from the volume element again. So what this turns out to scale as is B to the power 4, lambda to the power 5, and that has to be constant. So that's what this conservation of fluctuating helicities gives you. And if one plugs that scaling relation into the coefficient of k to the 4 in that spectral expansion I showed before, one finds that b squared lambda to the 5 goes like b to the -2. And so sure enough, we predict the inverse transfer. And as b decays, this thing has to, that's because as b decays, this combination b squared lambda to the 5 goes up. And so here's just some numerical evidence to confirm that this picture is the right one or believable. So this is the evolution of the magnetic and kinetic energy spectra for this simulation, or the simulation of which this is a snapshot. So what one finds, so in blue you have the magnetic energy, which at all times stays dominant over the kinetic energy, and plotted at various different times. So what you find is, precisely as in the case of Brandenburg simulations, that this as the energy decays at small scales, the large scale asymptotic grows with time in the magnetic energy. So that's the inverse transfer. Whereas if you look at the power spectrum of the helicity, now that quantity, one can also ask, what is its spectral asymptotic? And I hope it's not a stretch, given that the Saffman integral was one of the coefficients in the spectral asymptotic of this. I hope it's not a stretch to believe that IH is actually the asymptotic of this spectrum, of the helicity power spectrum, just from precisely the same derivation. And in this simulation, which showed the inverse transfer, what we clearly see is no inverse transfer in the H power spectrum. And in fact, that H is very well conserved. And actually, it's extremely good conservation when you consider that this IH scales really is quite a strong, quite a large power of its sort of constituent B and lambda. So that means that if B and lambda are deviating even slightly from the power laws that this implies, this spectrum could really be expected to not look very good, but actually it is conserved really quite well. So that, I think, is one piece of the puzzle of what's missing from the canonical treatment. So this invariant wins, and so that invariant is a sort of detailed discussion that you'll find in the first paper that I linked to on my first slide.
Sorry, may I interrupt again?
Sorry, yeah, please.
Quick question. I was just curious about the end game when the time goes basically all the way to infinity, let's say. It seems like this suggests that everything goes into the magnetic energy. That would not be realistic, I believe. Something has to intervene. Your blue line will continue growing and growing.
Well, in the simulation, it's going to hit the box scale. In the case, in the real physical case, the kinetic energy is always maintained at some level that is set by the magnetic field. So I'm about to argue it's set by the reconnection outflows. So the kinetic energy is always kept at the level that is required by the process of merging magnetic structures. So you never find yourself in a situation where magnetic energy is huge compared to kinetic energy. Well, I mean, it's always larger. That's the fact. But yeah, kinetic energy is never absolutely zero.
Can I ask another question? In these simulations, do you start with the K to the 4 spectrum?
Yes.
Okay. What happens if you start with, say, a K squared spectrum?
So this is so now I know that the simulations by Repin and Banerjee, they find no inverse transfer in that case. So I haven't run simulations of the kind. I believe they're simulations. But I believe that, however, the inverse transfer still should occur. It's just that what should happen is that you have, and there's an appendix of my recent of the archive paper that lays out the reasoning for this. But what I believe should happen is that you have a k squared spectrum, and then you have a bit of inverse transfer, and so you have k squared transitions to k to the 4, and then that k to the 4 keeps growing. But in fact, if you go to small enough k, you always have k squared, and as that k to the 4 grows, the physics of that k squared becomes less and less important. But if you work out, so as I say, there's a theory of this in that archive paper, and if you take that theory to work out exactly how fast that k to the 4 should be growing, it's extremely believable that it would not be able to be seen in a simulation that wasn't absolutely enormous.
I see. Okay, very good.
Okay, if you like, at the end, I do have a couple of slides that go over roughly the theory of what all that's about, but maybe if we have time and there's interest.
Sure.
Okay, right. So aside from the invariant, the other question, or a second sort of point that I think deserves closer examination is, what is the decay timescale? So before, I sort of said, oh, well, it must be the alphenic timescale, as sort of historically has been the case. But actually, that's not necessarily true. So it's useful, I think, to recall what the physical meaning of magnetic helicity, this quantity that I've been talking about. The magnetic helicity is a topological invariant, of course. That is, but what's special about it is that it's actually preserved even when the magnetic field lines reconnect with each other. So magnetic helicity it's the linking number. So when you have two linked magnetic flux rings and they unlink, they reconnect, so they change their topology, nonetheless the magnetic helicity is conserved. And the way that happens is that the linked flux rings become a single ring, but that single ring is twisted, so that linkage becomes a self-link. And so overall, the helicity you'll find in that process is conserved. Now, of course, helicity is only the special quantity that is preserved even when magnetic fields are, that's only a special quantity if magnetic field lines are actually reconnecting. And so the basis of the theory of MHD, or the conventional theory of MHD relaxation, which is often called J.B. Taylor relaxation, the relaxation subject to net helicity, is that you have a bunch of magnetic field lines. They're continuously reconnecting. The fact that they reconnect allows them to drive flows, because of course, if you imagine that you have a magnetically dominated stochastic magnetic field that's all very tangled up, there's no guarantee that it has the freedom to drive flows. So those flows can only magnetic energy can only generate kinetic energy if it can break its topology, if it can reconnect. But the point is that those reconnections preserve helicity. So that's the physical mechanism. That's the physical reason why magnetic helicity is an important quantity. But what this means for us is that actually the decay timescale, maybe that's confusing. The decay timescale should be the timescale for magnetic field lines to reconnect, for the topology of magnetic fields to be broken. And that is the timescale that we should be including in these decay theories. So I'll provide some numerical justification for that statement on the next slide. But let me ask, what is that timescale? How does one work out the timescale for reconnection? So within the framework of magnetohydrodynamics, the simplest theory of this is due to Sweet and Parker, the Sweet-Parker theory of magnetic reconnection. The idea is that you form very intense, very narrow current sheets, and then you have an inflow of plasma carrying magnetic field. Those magnetic fields enters a very narrow region where magnetic diffusion becomes important because gradients are very large, and then these field lines reconnect, and you have some kind of outflow that carries the reconnected magnetic field away. Now, the time scale for that process is derivable just using sort of simple twiddle arguments based on incompressibility, or really based on mass conservation, based on this being an efficient steady state process, and it turns out that just applying some twiddle arguments will give you that the decay time scale is not the alphenic one. You'll see the alphenic one there, lambda over VA. That's the time scale we had before. It's not quite that. It's that multiplied by this dimensionless number, s to the power of a half. S here is the Lundquist number. So that's the Alfvén speed times lambda, the scale of the current sheet, divided by the magnetic diffusivity. So this is the sort of Sweet-Parker theory, and it gives you slow magnetic reconnection because, of course, this depends on the magnetic on the magnetic diffusivity, which usually in astrophysics and certainly in the problem of decay of primordial fields that we're talking about is very, very small, and so this process is very, very slow. Now
you are saying that even like in that diagram with the linked flux tubes, that the reconnection will preserve the helicity because the linking will go into the twisting.
Yes.
Somehow I was under the impression that the theory was that if you have a random volume, there'll be reconnections, but sometimes they'll increase the helicity linking and sometimes they'll decrease it. And on average, you get helicity conservation. That's not.
I mean, I guess that's basically the same statement, but I mean, I think it's the case that as you make the resistivity smaller and smaller, as you make the Lundquist number larger and larger, the amount that you change the helicity during every relinking goes to zero. It becomes it's not just a statement of, you know, some of them make it larger, some of them make it smaller. Actually, you know, when you do get yourself into this asymptotic regime, you preserve the helicity.
I see.
Actually, may I clarify this thing?
Sorry, Brandenburg and company have done some simulations of these linked structures, right?
Yeah.
And they've, I think, remember the helicity was always conserved.
Yeah,
Okay.
I mean, you can never find it. So that, I mean, to be honest, that's the reason that you do see a slight, you know, you could argue that there's a very slight decrease in this H power spectrum. That's because, you know, any finite thing you can do in a simulation, you will never be able to preserve the helicity exactly. But if you go to, and indeed, if the magnetic diffusivity is quite large, you won't preserve it at all. But yeah, if you make it small, then it should be conserved.
I know Igor has a question.
Yeah, I just wanted to clarify this point because it was confusing to me too. My understanding is that only in the limit of infinite conductivity, this is strictly correct. If the conductivity is finite, you will have electrical field and E dot B will necessarily change helicity.
That was not my understanding, but perhaps, well, I'd be interested to talk more about this, but that isn't how I understand it. It was my understanding that helicity becomes a better and better invariant as you make Lundquist number larger and larger.
Well, it's essentially, again, the exact conservation only when it's pure magnetohydrodynamics E exactly zero. E dot B is by definition dt of integral A dot B.
Yeah.
So as soon as you have electrical field parallel to the magnetic field, you will necessarily change helicity.
Yeah, okay, well, I mean, yes, you will. Okay, I take your point. You will have small but finite, at any finite resistivity, you'll have dissipation of the magnetic helicity. But the question is, what does small mean? And I think the point that can be proven via sort of Cauchy-Schwarz inequality-based arguments is that the time scale for helicity dissipation is asymptotically long compared to the time scale for energy dissipation.
Well, that might be true.
I think that's it. And so therefore, when you're trying to theorize about the decay of energy, you know, on a time scale on which the energy dissipation is finite, the helicity dissipation you can take to be zero, I think.
Okay.
Right. So, okay. So this is this sort of picture here. This is the theory of Sweet and Parker, where you have reconnection, but it's slow in the sense that it depends on the magnetic diffusivity of the medium. Now, it was later realized that actually these current sheets that are formed during the formed as part of the Sweet-Parker theory are actually unstable structures. They're unstable to a resistive instability called the plasmoid instability, which was, I think, discovered by Shibata and Tanuma, and later sort of rediscovered by Loreo et al., and later realized that actually what this instability does for you is gives you fast magnetic reconnection, which is magnetic reconnection within the MHD framework, magnetic reconnection that does not depend on the size of the magnetic diffusivity. And that's because your magnetic structures that are formed as part of the instability, so-called plasmoids, are break up the length of the current sheet becomes smaller, and then between those plasmoids you have a smaller current sheet, which is easier to force material into, and then that current sheet can also become unstable to this plasmoid instability. You can have a hierarchy of plasmoids, and basically what turns out to matter within this theory is the reconnection rate associated with the smallest plasmoid layer within the hierarchy, which is the plasmoid layer that forms at marginal stability, which is marginal stability being the case where the Lundquist number associated with the sheet scales like 10 to the 4. So the upshot of all of this is that the reconnection timescale needs to be updated to be the minimum out of the Lundquist number to the half and the critical Lundquist number to the half, where if S is very, very large, this just becomes the critical Lundquist number, which of course doesn't depend on the resistivity. And so SC to the half is just 10 to the 2. And so one finds a moderately or a decay timescale that is longer by a factor of 10 to the 2 than the one that you would have originally thought. Okay, so that's fast magnetic reconnection within the MHD framework. Now,
quick question.
Yes.
Helicity is still preserved in these plasmoids?
Yes.
I thought not. Yeah?
Yes, I think so, yes.
Okay.
Yeah. Now, actually, within one further modification needs to be made, because this is because basically these expressions here assume that the dynamics of the current sheet is basically a balance between magnetic tension force and inertia of the fluid. But in a large Prandtl number plasma, where the Prandtl number is the viscosity divided by the resistivity, actually that force balance is between tension force and viscosity, because you meet the viscous scale before you meet the resistive scale. And so that means that you have to bring a factor of basically Prandtl number in everywhere. And so the sort of fully generalized version is to put a factor of 1 plus the Prandtl number to the half. So if the Prandtl number is small, you just get the same thing that I had before. If the Prandtl number is large, there's just a Prandtl number to the half factor here, and then S is also corrected by a Prandtl number. So again, so now in the large Prandtl number case, things do again depend on the resistivity of the medium, but only via the Prandtl number. So those scalings are derived in the Shekshikin's review of MHD turbulence in one of the appendices. Okay, so that's the decay timescale. So now let me, as promised, just provide some numerical evidence for this decay timescale. So the fact that reconnection is the governing process in these decays is I think not a new statement. I think this statement features in the papers of Biskamp and Muller going back to sort of 1999-2000. But I think it's only recently been shown that actually the presence of reconnection can be detected in the decay power laws in the decay of magnetic energy. So this was, I think, first done in 2D in 2019 by Zhu et al., where they looked at this decay of 2D MHD turbulence. So that's basically magnetic islands, and you can see from sort of the picture that this is actually not their picture. This is just a simulation that I ran. You can see that you have mergers of magnetic structures. Then if you watch a video, you see that this is basically the dynamics. And so the reconnection there is just apparent. And what one finds is that if one plots energy, magnetic energy is a function of time at different Lundquist numbers. So that's what they do. So this is the inset. Magnetic energy is a function of time at different Lundquist numbers. One finds a sort of array of different curves. But if one renormalizes time in all of these curves by the initial reconnection time scale, all these curves sort of lie on top of each other nicely. And it turns out this very much doesn't happen if you just renormalize to the magnetic diffusion time scale, which is a distinct time scale and tells you that really it's reconnection that's going on, not magnetic diffusion, and certainly not, or apparently not, standard alphenic motion. So the fact that they lie on top of each other tells you that actually this is a reconnecting process. Now, actually, in 3D, a couple of years later, the same group, this time Bart et al., 21, showed the same thing for non-helical 3D MHD turbulence. So you have now a range of Lundquist numbers in a 3D simulation, and you have a splay of power laws. And then if you rescale by that, in this case, the Sweet-Parker reconnection timescale, you find that these things sort of line up with each other reasonably well. To the extent that they don't line up with each other, that's due to imperfect helicity conservation at low Lundquist numbers, where S is not large enough. Now, another way actually that one can verify the role of magnetic reconnection and what was used in Hosking and Shekshik in 21, we showed that actually if you employ a modified magnetic dissipation operator, so this is a hyperdiffusivity, if you essentially, instead of having Laplacian dissipation in your MHD equations like a eta Laplacian of B term, if you promote the Laplacian to sort of like a nabla to the 4, nabla to the 6 hyperdissipation term, then if you use the Sweet-Parker theory, you can work out exactly what your decay power law should be in that case. And indeed, if you look at your simulation, you take those and you measure what that power law is, indeed, the power laws become those laws that depended on your modification to the dissipation operator. So that is I guess a slightly more subtle argument, and so I've just sort of put that in text there. But you'll find that in the in the paper that I referenced before. So I should point out that actually that is the case both for helical and non-helical initial conditions. This isn't a peculiarity for non-helical fields, and by the sort of and that's to be expected, because sort of my point here is that the helical and non-helical cases are really sort of governed by the same physics, both of them by the physics of helicity conservation via reconnections, which is to say that dominant physics is reconnections. It's just that in the helical case you have an abundance of one sign of helicity, in the non-helical case you just have fluctuations, but the sort of physics is the same. Reconnection. Right, so we're getting close to the hour, so I should probably get to the point that I've been building to. So how what does this theory imply for the decay of the primordial field? So let's use this decay time scale tau for this reconnection theory. It comes from the reconnection theory. Now that there is one last physics subtlety here, which is how does one compute the Prandtl number for the primordial plasma? Now, the question is what one takes for the viscosity, because there are two regimes within this plasma. So if the mean free path of the proton motions is much less than their Lama radius, which is to say the limit of weak magnetic field, then everything is just sort of standard plasma viscosity, and one goes with the standard Spitzer theory of plasma viscosity. However, if the Lama radius of the protons is much less than the Lama radius, is much less than the mean free path of the protons, that means that those protons are completing many Lama orbits between each collision, and that suppresses motion of protons across magnetic fields, and so viscosity becomes an anisotropic tensor, and in particular, the viscosity across the field lines is suppressed by a factor that's the Lama radius divided by the mean free path squared. And that's so-called Brzezinski MHD theory. And so there's a suppression from the Spitzer estimate. Now, actually, that characteristic, that critical point where the Lama radius becomes comparable to the mean free path actually turns out to happen right in the middle of our phase plot. So this is an important thing to know about. So basically, this is the generalization then with the new theory of that plot that I showed you earlier, the B tilde versus lambda diagram. The new locus of modern day field states is shown by this blue line. So basically, the transition happens at this critical magnetic field. This is B scales like B iso, where B iso is just the critical magnetic field to make the Lama radius equal to the mean free path. So below that magnetic field strength, one follows this line with PM set by the Spitzer PM. So that's just MHD, sort of honest to goodness, what you'd expect for MHD. Then above this B is like B iso. You have to put this factor of RL over lambda mean free path into PM. So of course, RL depends on B. So now you have an extra power of B on this side. And that actually changes the gradient of this line. So it becomes a little bit shallower. And then actually another thing happens when you get to magnetic fields that are around about 10 to the minus 11 Gauss in strength. What actually happens is that this quantity that I denote delta C here, that's the critical scale associated with the bottom of that plasmoid hierarchy that I talked about, becomes comparable to the plasma ion skin depth. So that's basically the scale at which the ion and electron motions within the plasma decouple, and MHD is no longer a good approximation to the dynamics. So one has to do proper plasma physics in that scenario. And typically outside of fluid theory becomes dodgy. And usually what one finds is that magnetic reconnection becomes fast and independent of the fluid PM, certainly in that scenario. So that leads to basically a further flattening off of this line. But actually, that only happens for exceptionally energetic fields at the phase transition and large scale fields. So I think one can probably safely neglect that physics. So basically, this is what one finds: a large range of initial conditions that would produce magnetic fields that are comparable and exceed the observational constraint. So this theory has allowed helical fields now to terminate within the non-helical fields to terminate within the allowed region of the phase space. So this is the condition that the magnetic field strength at the phase transition T star divided by, that's 10 to the minus 5.5 Gauss, that's the characteristic co-moving field strength that would correspond to magnetic energy and radiation equality, multiplied by lambda, to the power 4, because of course this thing is b to the 4 lambda to the 5, so that's why the scaling is like this. So multiplied by lambda divided by 10 to the minus 10 megaparsecs, that's RH. So maybe it would have been better to put RH here, but that's RH. It has to be greater than 10 to the minus 23. So what this basically says is that you have wiggle room on both of these sides. You can make, if you like, you can make B a factor of 10 to the, well, I should say you can make lambda a factor of 10 to the minus 2 smaller if you like, and then you still have quite a lot of wiggle room within the magnetic field strength below that theoretical maximum, where you can still produce magnetic fields that are consistent with the gamma ray observations. Now, there is one last subtlety that I guess I should mention, which is that there are, I've sort of presented this. Oh, of course you have to suppress your viscosity, but this, in the decay of magnetic fields in a pressure anisotropic plasma like this is, a plasma where you have an anisotropic viscous tensor, such plasmas are subject to sort of certain instabilities, and the presence of those instabilities can, or in principle, could adjust the picture of the decay. This is not, I think, a well-studied thing. In principle, these instabilities, well, so I guess what I'm trying to say is, what's the most extreme thing that these instabilities could do, given that we don't understand them? Well, the most extreme thing they could do is actually make this PM small, if they're present, because the fact that this B is that these dashed line is large is a consequence. Is increases as it does, is a consequence of the largeness of PM. So let's now just make let's back up a bit and make a sort of maximally ignorant estimate and say, well, let's just let the PM be 1. What would the corresponding states be at the present day? And that's what's shown on the red line. And actually, you find that that's consistent too with the observational constraint. So even subject to certain plasma instabilities that are not well understood, one cannot, this doesn't affect the qualitative picture that I'm trying to explain here. Now, I should also say that I have, as one of the appendices of the paper, a sort of simple calculation that is designed to show that these instabilities shouldn't actually be triggered. So one can show that the decay of the magnetic energy is sufficiently slow to avoid the criterion for instability in these pressure anisotropic plasmas. But I will say that this is not a well understood area, and so potentially further work to follow on that topic. Right, so there we are. Sorry, I'm 5 minutes over, but this is the conclusion. We present 2 modifications to what you might call the conventional, and this is the Banerjee and Jadamchik treatment of decaying primordial magnetic fields without magnetic helicity. The first one is that this selective decay of small-scale structure shouldn't hold for decaying MHD turbulence, and that's, I guess that's not a new statement. This was shown numerically by Brandenburg, by Zrake, but what I want to say is that the scaling relation that is implied by that and its generalizations for the fields, this is coming back to Tanmai's question earlier, should be replaced by the one. This is sort of the missing law. This scaling relation should be replaced by the one implied by the conservation of IH, which is this b to the 4 lambda to the 5 is constant. The decay time scale likewise needs modification, and it's limited by magnetic reconnection. And so this makes the energy decay much slower than if it occurred on the alphenic time scale. And so what the combined effect of these 2 things are is a significant increase in the expected strength of the primordial magnetic fields at recombination. And what this does is it brings the it brings the possibility of non-helical magnetic fields being generated at the electroweak phase transition into consistency with the gamma ray constraints on the void fields. So that's something that wasn't the case before, but with these 2 modifications, you find a nice consistent answer. So thank you very much for your attention, and thank you very much for your questions as we've gone along as well.
Thank you, David, for the nice talk. Questions from the audience?
So one question is, you said that you needed fluctuations of helicity.
Yeah.
In the initial state.
Yeah. What happens if I don't have them?
Yeah.
Yeah, that's a great question. This is actually when I completed the original paper, the first paper, I presented it to Kandu Subramanian, and he asked the same question. So I went away and thought about it for a little while, and actually I ran a simulation. So I ran a simulation of a magnetic field that had pointwise 0 helicity. So that's actually not an easy thing to do. So like a Gaussian field, it can be shown, has this invariant. This invariant is maximal for a Gaussian field. But to have this invariant be 0 every way, one has to really make quite a synthetic field. So an example of such a field would be just little unlinked rings. So you'd have a little sort of Cheerio, if you like, no twist in it, and then you just replicate that through all the space. None of these little loops are allowed to interlink with each other. Now, what happens if you set that up and then let it go? Well, what turned out to happen, and this is detailed in one of the appendices of this paper, is that the evolution looks completely different to the sort of standard evolution of a non-helical magnetic field that people usually study, because people usually study them with this IH is non-zero. But the evolution looks completely different. What happens is the magnetic fields are not constrained by their topology. They don't have to reconnect. There's none of that going on. They simply just shrink. They relax to 0 magnetic energy or close to 0 magnetic energy. So their energy massively goes down. They drive outflows. And then you have a dynamo. And the dynamo regrows the magnetic field back to something like equipartition, or as close to equipartition as you could reasonably expect to achieve in a finite resolution. This wasn't a huge simulation. And those regrown magnetic fields, of course, have the helicity fluctuations. So my conjecture is, and of course, my simulation was sort of finite resolution, but my conjecture is what's likely to happen is the magnetic, the velocity field is likely to regrow. What should we expect if the Reynolds number is large enough? The magnetic field via dynamo, the velocity field via dynamo should regrow the magnetic field at the integral scale. Ultimately, the saturation will bring the magnetic field back to the integral scale. The energy should be comparable to the kinetic energy. So basically, the system retains knowledge of its initial magnetic energy, because the magnetic energy is all converted into the kinetic energy. The scale is the scale of the flows, and then the flows grow the magnetic field. And so actually one finds oneself in a situation that is very similar to if one had just started with IH is non-zero. In my simulation in this process, the value of IH that you get is something like 10 to the minus 4, 10 to the minus 5 of the IH that you would have had you started with IH maximal, which is a lot, 10 to the minus 5. But on the one hand, that's, as I say, that's a finite resolution simulation. And on the other hand, 10 to the minus 5 is really not very much in terms of these values that we're thinking of here. Like we're talking about a range of 10 to the minus 23. And so if this IH drops by a factor of 10 to the minus 5, well, you're only gonna put yourself from here over slightly over here on the left. Actually, the answer to your question seems to be the field just reorganizes itself into a situation with IH is non-zero. Then, of course, once IH becomes non-zero and the magnetic field is concentrated at the large scales, then IH gets fixed because the magnetic field at the integral scale is no longer allowed to decay magnetic helicity.
Now,
so it decays than as before.
From the electroweak context, you expect helicity fluctuations. I mean, because it's also linked to baryon number. You can produce baryons, you can produce antibaryons. So it should be a mix. But Igor has a hand up. I spoke out of turn. Sorry, Igor.
No problem. Actually, it was great talk. Thank you so much. I have a simple question. I'm not sure if this is directly related to the mechanism you're proposing, at least indirectly. When you were giving the motivation, you were basically saying that the dynamo due to the structure formation is out of question, and then you explained why. My little problem with that is that all of this, what you're saying, is basically happening way before the structure formation. So the structure formation comes later, and it can interfere in the middle.
Yeah.
So, and in principle, those voids form from the structure formation. So my simple question is, if you do have some dynamo mechanism during the structure formation, it will still modify whatever you have before that. Isn't that correct? So it's not true to say that it's completely excluded.
Yeah, I think that's right. But I think, you know, one could, I think it's likely to be quite different. The amount of dynamo that you have within a collapsing structure to the amount of dynamo that you have in a void that's kind of, you know, just being left by the, flows would, but I guess my point is you don't need any dynamo action. You know, you don't have to rely on any flows. I mean, of course, to have a dynamo, you don't just need a velocity field, you need a shear. And you need some kind, and I don't know whether that shear is sufficiently large.
Okay, so maybe to reformulate, is there possibility that there is dynamo during the structure formation, and other estimates how big it is?
I must say that I don't know the answer to the question of how big it is. What I know is that these sort of usual treatments of this decaying field would exclude it. But I think there are studies that look into the possibility of weak dynamo amplification, basically motivated by the fact that, you know, you can get fields that are within the disallowed region, but perhaps if you had a little bit of dynamo there, maybe that could bring you up a bit. But I mean, it's a bit of a nasty fix, because if you had dynamo, then you the whole mechanism of the decay is irrelevant anyway, because dynamo is going to grow you to a value that's independent of the seed. So yeah,
there are high redshift galaxies, maybe a redshift 6 or something, which are also observed to have magnetic fields of about the same strength, and they have only rotated 5 or 6 times or some small number of times, so there's not much dynamo amplification.
Okay.
Yeah.
Any other questions? If no, let's thank David. Tammy, do you have a question?
Thank you very much.
Yeah, thank you.
Great work.
Thanks very much, everybody. Thank you very much for your questions as well.
Thank you. See you.
Bye.